Hi guys, Miss Francis here. I'd like to finish up today's discussion on osmoregulation by focusing on the nephron, which is the functional unit in our kidneys. So if you follow along with me, I know this is very wordy, but I'm going to lead you as we go through it. So if we first look at number 3. Number 3 is the renal artery, where unfiltered blood is going to be brought to the kidney through this vessel. So number 3 is the renal artery. From the renal artery, our blood is going to travel to structure 2, which is the afferent arteriole. It's just a smaller tube, meaning it's smaller than the renal artery. From there, number 1 is the renal artery. From there, our blood will travel to structure 3. Structure 3 is the glomerulus. The glomerulus is a knot of capillaries. It's a bed of capillaries. It's a bundle of capillaries. This is the site of ultrafiltration, meaning that small molecules are going to be able to filter out of glomerulus and go to the Bowman's capsule. So that is structure number 4, Bowman's capsule. Ions such as sodium and potassium, salt, urea, water, glucose, those will all be filtered from the blood in the capillaries in the glomerulus to our Bowman's capsule. And now the liquid that's in our nephron is called filtrate. From there, our filtrate's going to head to structure 5, which is the proximal convoluted tubule. Sometimes it's just written as the proximal tubule. This is where reabsorption is going to occur. So you see these white tubes. These white tubes are capillaries. All of these capillaries are surrounding the nephron. And that's important because the materials that we originally filtered out of our blood, some of those are needed. For example, we need glucose to do cellular respiration. We need sodium and potassium in order for our sodium-potassium pump to work correctly. So we're going to reabsorb some of those molecules that we originally filtered out. So they're going to be reabsorbed from the proximal tubule into those capillaries that surround the nephron. From there, our filtrate is going to head down the loop of Henle. Now be careful. Some pictures show the loop of Henle with the descending side on the right and the ascending side on the left. Some pictures show the reverse. So you really need to know how to trace the filtrate through the nephron. On the descending side of the loop of Henle, your your loop is only permeable to water, whereas on the ascending side, it's only permeable to salt. So salt is going to be released into the medulla, because remember I said that the nephron stretches across the cortex and the medulla. So if you look at this blue dashed line, that's the imaginary line that separates the cortex, the renal cortex, from the renal medulla, where part of the nephron is in the cortex and part of the nephron is in the medulla. Well, when this salt gets actively pumped out of the loop of Henle, it creates a hypertonic situation in the medulla. So the water wants to diffuse out into that hypertonic environment. So from the loop of Henle, our filtrate is going to travel to structure number 8. And that is the distal, I know that's kind of hard to see, it's a D, distal convoluted tubule. This is where secretion occurs. We're going to get the last bit of water and the last bit of ions out and put it back into our blood before it heads to our collecting duct and gets released as urine. Let's take some notes now on the steps of making urine. So you're going to have ultrafiltration occurring at the glomerulus and Bowman's capsule. The small molecules are going to enter the Bowman's capsule from the glomerulus, and now it's called filtrate. But Large molecules such as proteins and red blood cells are not going to be able to be filtered from the glomerulus to Bowman's capsule. Those larger molecules, those proteins, those red blood cells, are going to leave via the afferent arteriole, and they're going to stay in the blood. Reabsorption is going to occur at the proximal tubule. Molecules like glucose, salts, they're reabsorbed or reclaimed back into the blood. So remember from our last unit that glucose is going to be co-transported with sodium. And the reason why you have these surrounding capillaries is because those are the blood vessels that are going to do the reabsorption. So here's a picture showing the filtrate from Bowman's capsule as it's flowing through the nephron and the collecting ducts as it becomes urine. Now look at this picture. Notice that the descending side is on the left and the ascending side is on the right. It's opposite in our picture. So just be mindful that different pictures can represent the loop of Henle differently. So now if we were to take a closer look at that loop of Henle, you see that the salt, the sodium gets pumped out via the sodium-potassium pump. Our renal medulla becomes salty, becomes hypertonic, and that enables the water to follow by diffusion. It's going to exit via aquaporins, so it will do facilitated diffusion. Then we head to the distal tubule where the blood can finally reclaim the last bits of water and the last ions before it gets removed from the nephron as urine. So the last step involves the collecting duct. The collecting duct is where that urine collects. Now, ADH is a hormone that plays a vital role in osmoregulation, determining the amount of water that's going to be in your urine. ADH stands for antidiuretic hormone, and what it does is it opens aquaporins to absorb more water into the blood. So for example, if I just played an hour-long soccer game and I didn't take one break, I might be dehydrated. Well, I don't want to go to the bathroom and lose any water that my body might need to hold on to try and stay hydrated. So what I'll do is I'll send a message to the pituitary gland, which will release ADH, telling the aquaporins to open up and reclaim that water back into that blood so that the water is not released out of the body in the urine. Lastly, you end up with the urine that's going to exit the collecting duct. So that ends our discussion on osmoregulation.